Hello, and welcome to my talk, Hacking Kubernetes and Protecting Yourself Against It. In the next 45 minutes, I want to first introduce you to some basic container and Kubernetes security considerations, and then directly dive into a simple web application as a demo where I'll show you how you can hack into that application by exploiting a security vulnerability in it, and how to then take over the container, the complete Kubernetes cluster, and the cloud provider account where the cluster is hosted. After that, we'll go back and see how, step by step and layer by layer, we can protect ourselves against all these different attack vectors. Before we get started, a short shout out to two people, Nico Meisenzahl and Kos. Kos created the demo application that is vulnerable to an exploit that I'm using as part of my demo. And Nico Meisenzahl gave an inspiration for this talk by doing a similarish talk last year on a couple of conferences where he also hacked into application running inside of Kubernetes. But I'm focusing way more on the remediation of these attacks and how to do this with zero trust tooling. So, a lot of applications nowadays run inside of containers in production in Kubernetes. And that has influences also on security. In terms of security, there are two things we have to consider. The security of the Kubernetes cluster itself and the security of your containerized applications running inside of these Kubernetes clusters. The Kubernetes cluster itself is already also a high-value target for attackers. Because if an attacker finds a security vulnerability within Kubernetes, they can not only exploit and attack one system, but hundreds and thousands and tens of thousands Kubernetes clusters out there. So it is important to also configure your Kubernetes cluster according to best practices and keep it up to date. Things to consider there are who has actually access to the Kubernetes API and also with which permissions. So configure role-based access control correctly and accordingly. You want to look into certificate management, both for application TLS certificates and the Kubernetes internal certificates. Kubernetes needs to be up to date so that you patch any CVEs that have been found. And you also may want to limit what the applications and containers in your clusters can do with admission control and security policies. The Kubernetes data store, etcd, can be encrypted, and you can also limit network traffic inside of your clusters and encrypt it if necessary. But it doesn't stop there. Your applications yourself are also vulnerable. And if we look into a highly dynamic Kubernetes environment where containers and pods can run sometimes on this node and sometimes on this node, scale up, scale down, do rolling updates, do blue-green deployments, and all kinds of dynamic things, which is the reason why we're actually using Kubernetes, a lot of the traditional security tooling does not work very well in these dynamic environments with these ever-changing IP addresses and amount of instances. Because of that, oftentimes what you see is that a security boundary is cut around the Kubernetes cluster, where everything that is running outside of the Kubernetes cluster is deemed as not trusted. And then there is an application firewall and other things around this. And on the other hand, everything inside of the cluster, all the pods running there, are considered completely trusted, and it's a Wild West in there. That's actually not quite good. The firewall is fine around the cluster. Restricting what can get into the cluster and get out of the cluster is good. But there can also be malicious actors inside of the cluster. It could be that some internal developer is acting maliciously and attacking the cluster and other applications from the inside. If it's Wild West in there, if there are no restrictions, they can just do that. It could also be that application inside of the cluster that is exposed to the internet has a security vulnerability and that is not caught by the web application firewall. And then through layered attacks, you can in the end take over the complete cloud provider account. You will see that in the demo. So the better approach would be to basically consider everything as not trusted and cut a security boundary around every and each of container inside of the cluster. And we'll look in detail in this talk how to do this. On a technical level, things to consider there in terms of application and container security are: what capabilities are you actually giving your containers? Are they, for example, allowed to change the networking stack or not? Are there any compliance issues, too broad file persistent permissions, or maybe applications inside of the container processes running as root? And do the container images have any known security vulnerabilities and CVEs, either in the base image, in the installed packages, in frameworks and other libraries that you're using? Or do you even have bugs in your own software that you programmed yourself that can be exploited? To showcase all that, I brought a demo application with me. The demo application is a simple web app written in Java. It's exposed through an ingress and the ingress controller to the internet and running in the default namespace. The application doesn't have any kind of special service account. It is not allowed to access the Kubernetes API with any kind of permissions. But there is a DigitalOcean cloud provider controller running in the kubesystem namespace that is allowed to access the DigitalOcean API in order to provision persistent volumes and load balancers at the cloud provider. But these are all disconnected systems from each other. So let's see what we can do to hack into it. First, let's have a look at the application. So in here, we have RK1 123.16 Kubernetes cluster. Not the most recent version, but also not completely old. I have an application running in here as a deployment, which is my sample app. And if we just have a quick look at the configuration of the sample app, it's basically Kubernetes defaults. So we don't have any service account attached to it. Also, the default service account of the namespace doesn't have any elevated permissions. It's also just exposing port 8080 inside of the cluster internal network. And one thing maybe that is not that nice, the process is running as root inside of the container because it is necessary for the application to start. And we will talk about this in a bit at the end. The application itself is also exposed over an ingress. In that case, the ingress is actually not exposed to the internet directly, but on like an internal network because it is a vulnerable application with a security problem. I didn't want to expose this to the internet. I didn't want anyone else to hack into it. It's just me that I wanted to be able to hack into it. And of course, the ingress will then target a service. We can also just have a look at the application very quickly, and you can see it is a small web application with a login form. Let's also quickly look at the source code of the application at one of the Java classes there. This is the post endpoint that handles the login form. And you can see it is demo code, so it's not doing any kind of validations. But if the username is not admin and the password is not password, it will log the username and the user agent to standard out using the log4j logging library. So let's see what we can do there. Let's also go back. I also prepared a couple things here on some virtual machine that I'm using as an attacker. So I have one VM. This VM is running a small LDAP and a small web server that provides some malicious code. And I also have two tabs here open for various that listen to various remote shell connections that may be executed. So let's do, first of all, a small request to our application. And we can see, yes, that works. We can reach our application and we get the message back that the password that we entered was invalid. We should also see, if we go back here, that inside of the logs, we get some information back that curl just entered a weird or wrong password. So let's do the same request, but with an additional user agent header in here. So what is this? This is doing, it's sending a post request to /login with username test, password invalid, and then it's sending a user agent header with a log4shell vulnerability payload. And this is connecting the LDAP server that is on my attacker's VM, which will provide malicious code, which in the end will then connect to one of the remote shells, the remote shell I have here, on my system. You can see this request is hanging at the moment. That is because I have now oh, hang on 1 second, it's hanging, but I provided the wrong IP address. Let's quickly fix that. Okay. So this is the correct IP address. So it's still hanging again. And you can see I actually received a connection in my netcat here. And now I have a remote shell inside of the container. So I can start executing commands. For example, I can see here with PS, this is my Java application running. I also see my shell process and my PS process. And I can start investigating things in here and start to modify the container. But I'm still in a container. So first, let's maybe try a couple things. Let's maybe try if we can download kubectl. Maybe we have a service account that actually can connect to the Kubernetes API. So this command here is downloading kubectl and putting it to user bin. So kubectl is now installed. Let's try if we can do a kubectl get pods. And as expected, we actually get back that our service account that this pod is using is not allowed to access the Kubernetes API and list the amount of pods. Okay, let's see if we can do something else. Let's look at the capabilities that our container has. And we can see here, we have a couple capabilities, but these are only the default capabilities that any container has. And especially, we don't have any sysadmin capabilities that we could maybe use as a privileged container to do some more. Let's see if we can actually exploit a kernel bug that gives us more capabilities. So this is exploiting it, and let's see if we actually got now admin capabilities. Yes, we have. So now we have actually a privileged container. And there are a couple of things that we can do with privileged containers. For example, we could try to also exploit a bit of a kernel vulnerability and see if we can create an additional C group, and through this C group and some release notification execute a custom command. Not in the container, but directly on the host. So let me do some preparations. The details are not that important. I'll provide a link to a Git repository with detailed explanations of what all these commands are doing at the end of the talk. So I need to create a C group and configure some settings and create a small script. And this small script here is actually running SOCAT. SOCAT is also creating a remote shell on my attacker VM and connecting to another remote shell there, so that I'll have a remote shell in one tab to the pod and in one tab to the node. And let's now try to trigger this script. And if everything worked and we go back to this tab, we now have here also a remote shell, but this remote shell is now not into the pod, but directly on the node. So first of all, I am root here. We can also see with PS, there are tons of like Docker processes here from the RK1 distribution. So that all worked. And we can also do a Docker PS and see all of our Docker containers that are started here by RK1. And we even will also see somewhere here our Java application container, which I'm not finding, but it's in there. So, here at the top, the vulnerable application. So what else can we do with that? We are now root on the host. Let's try also to get admin access to the Kubernetes cluster. So I know, since this is an RKA-R1 cluster, that there is actually a kubectl binary inside of the kubelet container. So the kubelet container is this one here. So let's maybe copy the kubelet binary to our host system. That worked. I can now access kubectl, and I could say kubectl get pods, and then it says, okay, there I can't connect to localhost 8080 because the Kubernetes API is not running on port 8080, but on port 64.3, and I also don't have any configuration, no kubeconfig that gives me access to the cluster. But I know that the kubelet needs to access the Kubernetes API, and let's maybe see if we can copy the kubeconfig from the kubelet to our host system so that we can use it here. So here I have a command that I just executed that does this. It basically inspects the kubelet container, looks at the mounts, and finds then a kubeconfig in there, and in the end stores this as kubeconfig admin.yaml. So let's tell kubectl to use this kubeconfig. And now, if I say kubectl get pods, I actually get all my pods back. Let's maybe look at the secrets in the kubesystem namespace. You can see there is a DigitalOcean secret in here. So let's maybe look at the content of this. Yes, so as a content, it has an access token. So let's maybe extract this access token and store it in some environment variable. And let's see now if we maybe install the DigitalOcean command line tool on our host. If we can take this token that we just got out of the secret to log in into DigitalOcean. That worked. So let's try if we not only can take over the Kubernetes API of this cluster, but if we can also create an additional virtual machine at DigitalOcean. So again, what I executed here is doctl compute droplet create, and I created a VM in the Frankfurt region with 1 CPU and 1 GB of memory, and provided some SSH key to it. And that could be a VM that I'm using then for crypto mining or other things. Let's double check in DigitalOcean if this VM is being created, and yes, it is being created. So this will take a couple of seconds until the VM is up and running and ready. And there it is. I got an IP address. I could connect to it now, and we can even try this. So let's copy the IP address. Let's open up a new tab here, and let's just see if I can SSH into here. And yes, it worked. I'm root on a VM that I just created. Okay, let's go back to our remote shell. And just to clean everything up and to not create unnecessarily costs, let's also delete the VM again. So that was an attack. We basically very quickly could take over the cloud provider account. Let's recap what just happened. So there we had a sample app that had a look for shell security vulnerability. Through this vulnerability, we were able, as an attacker, to exploit it and get a remote shell into the sample app container. The sample app container was not running privileged, but we could modify the file system of the container, so we could install additional stuff, download binaries, create scripts, and so on. And through a kernel bug, we could also escape the container and get sysadmin capabilities. And also get then a remote shell as root directly on the host of the Kubernetes cluster. Because we had root access to the host, we were able to get an admin kube config, so we were also admin in the Kubernetes cluster. And we could read out the cloud credential secret in the kubesystem namespace that had a DigitalOcean API token to connect to the DigitalOcean API. And we were able to create a VM that we could use for all kinds of things like crypto mining. So that's bad. Let's fix it. To fix it, I'm going to use two tools. The first is Kubewarden. Kubewarden is a Kubernetes admission control tool that I can use to easily configure policies to prevent insecure resource configurations. For example, I can prevent privileged containers to run. I can prevent containers running as root. I can enforce read-only file systems and more. The second more important tool is NeuVector. With NeuVector, I can limit the capabilities of containers and prevent the deployment of insecure images that have known CVEs. NeuVector is tackling security at two levels. First, the supply chain with security and CVE and compliance scanning, and then runtime security, where NeuVector can limit what a container can do in production when it's running, to also limit and make all these attack vectors that we just saw not possible. There are a lot of more detailed talks about NeuVector, one also from Tracy here at SUSECon. You should definitely check it out if you want to have more details. Speaking about supply chain and scanning of images and for CVEs, this is vitally important because otherwise you are blind, you don't even know where the problems are. So the scanning part is important of NeuVector so that we know the CVEs, but it's definitely not enough because we may not be able to patch these security vulnerabilities right away. We of course should, but there are always reasons why we can't update something. Maybe there are some dependencies why we can't update our OS because some packages and libraries are not available. Maybe the team that handles the updates of the container image is currently on vacation. Maybe the CVE was announced on a Saturday and it's weekend. And it may take, even during weekdays, at least a couple of hours to patch something, test something, update it, and deploy it. Maybe it's a 0-day that is not even announced yet. Or maybe the development team can't update something because they have to rewrite the code first to comply to a new framework and library version. There are tons of reasons why something is running in production that has known or unknown security vulnerabilities, and we still need a way to protect ourselves against it. And that's where the zero trust runtime security component of NeuVector comes in. During runtime, NeuVector looks at all the processes that are being executed in every container. It looks at the network connections that are being made in and out of every container, both within the Kubernetes cluster and from and to the outside. And it's looking at all the files and directories that are accessed and being written to in every container file system. And then NeuVector can build up a rule set automatically based on the standard behavior that is necessary for the application to run. And it can then block everything else that is not allowed to run and not covered by this rule set. On the network level, NeuVector is not only looking at who can connect to whom, but it's also doing a deep packet inspection so that it can also check for known security vulnerability attacks, like for example Log4Shell, to also block these requests from reaching my application over a valid connection to begin with. Again, if you want to have more details on all of that, check out Tracy's talk about NeuVector at SUSECon. So let's fix it now step by step. In order to prevent all of that, we first need to install NeuVector. Installing NeuVector is quite simple. You can just do this from the Rancher app marketplace. And the only thing I'm configuring differently, because I have a small single node test cluster, I'm just booting up one replica for my scanner and my NeuVector controller that consists of or holds the NeuVector database. It's going to take now a couple seconds to install and start up NeuVector. We can also follow a bit along here and look at the pods that are starting up, and you can see NeuVector is now started, the enforcer started, the manager started, and the scanner started that's doing the scanning. The enforcer is doing the detection of the blocking on every node, the controller hosts the database and the API, and the NeuVector manager is providing the UI. Let's also restart our sample app container just so that we have a fresh container without anything installed so that we can recreate our attack quite simply. Next, let's go to the NeuVector UI. So NeuVector is directly accessible now from Rancher, and with a click, we can open up the NeuVector UI, accept the end user license agreement, and we can start maybe scanning our applications for vulnerabilities and our system for vulnerabilities. We can look, for example, on our nodes, and we can start the scanning of our very old Ubuntu 18.04 operating system. And if we now check the list of found vulnerabilities, we'll see, yes, it found the vulnerability that we just exploited to get elevated permissions. We can also have a look at our sample application container and scan this. And by the way, you can also activate auto scanning to automatically scan all of the assets in your cluster. And we can also see that NeuVector found that there is actually a log4shell vulnerability. Of course, you should patch this and update this, but let's say for the sake of this demo that you can't. And that's why you should use NeuVector's zero trust mechanisms to protect your applications. First, let's go to our sample app under policies, and to better illustrate that, let's switch off zero drift detection to showcase the learning a bit more. We can see, and maybe let's also execute here a request to our application again, which works. So let's go back to NeuVector, and we can see, if we refresh this, that NeuVector learned that there are a couple processes, like the Java process, that have been learned and executed here. And we also can see some network rules. Let's refresh this again. Some network rules that have been learned, for example, that external systems like the nodes for health checks and the English controller are allowed to access our sample app. So this is great. Let's now switch our workload to monitor mode. In monitor mode, NeuVector stops learning new things. It will not block anything, but it will alert us if anything is happening that is not covered by rules. So let's try our attack again. We have here a fresh remote shell up and running. Let's maybe put this up a bit and put this up a bit. And let's execute now our curl with our attack here again. So first of all, we got a remote shell here, and we can run ls. We can, of course, also download kubectl again. We can execute kubectl. We can't access the Kubernetes API. And we can also get ourselves, again, elevated permissions. Let's check if they are there. Yes, we now have kept sysadmin privileges. And let's now try to do the same exploit to get a remote shell inside of the node from our container. So let's create the command that executes socat again to get the container remote shell, and let's trigger it. And that worked, and we got our remote shell here as well, and we can now run docker ps and do all the things we did before. Let's also run doctl again. Yes, that all works. So let's go back and let's go to NeuVector. And the first thing we may want to prevent is that we actually run socat to create a remote shell from our node. And NeuVector can do this. If we look now at all the process profile rules, we see here that there is no socat learned. And if we go under notifications, security events, we actually see a lot of things. There is, for example, some suspicious processes that have been directed on the node. We detected that doctl, socat, bash, this is probably not something you want to run on the node itself. So we got an alert for that. We also saw that there have been violations inside of the container. We saw that it detected there has been a connection, an sh command, like an mkdir, a mount, a set, a capsh, kubectl, everything detected that it has been executed inside of the container, and it should not have been executed. It also has here alert that a connection to an external system has been made. This is the connection with curl to download kubectl. We also see here a connection that shouldn't have been there to an external system, which is my attacker VM. So all of that is already alerted. It hasn't been blocked. So let's start blocking. First, let's go to our groups here, and let's go to the node group, and let's add a new process profile rule to actually deny socat. Let's make sure that I copy and put the correct path in. So let's deny socat. And let's actually switch our node group, so the group that is used directly for the processes on the node, to protect mode. And let's try the last part again. So let's exit here, and let's, on my attacker VM, open up the socat port again. And let's just try to trigger the same process and the same C group again. You can see we did not get a connection here. We don't have any remote shell. And if we go back to NeuVector, to our security events, we can see that socat has been blocked on the node. Let's go further. Let's go and go back into our policies. Let's go to the sample app, and let's switch this one to protect mode. So let's not only alert, but let's also protect anything that is happening here. And now, if we go back to our shell, we can still type something here, but ls is not allowed anymore. kubectl is not allowed anymore. And if we go to our security notifications, we can see, we can see that you can see that already the network connection has been blocked to our external system. We could now allow this again and say, hey, we want to actually allow this connection, but yeah, that would be stupid. So we successfully blocked any kind of process execution as well as network connections to external systems there. Now, let's maybe try to block the request that exploits our log4shell vulnerability to begin with. And for that, NeuVector has also a web application firewall built in. And I already prepared a log4shell sensor here. So let's go to our sample app again. Let's go to the WAF rules and activate our log4shell sensor just for our sample app. And now, if we do the same request again with our log4shell payload, and if we go back to NeuVector, we'll get a security notification that a log4shell attack has been detected and has been blocked. And we even get a packet capture here that we can download and analyze, for example, in Wireshark to see and analyze and do forensics on this HTTP request that was just blocked so that we can maybe find out who the attacker is. There has been an additional problem with our application, and that is that we actually allowed this container and this application to run as root. And if we hadn't ran it as root, some of the exploits wouldn't even have been possible. We may want to prevent applications running as root. And for that, we can use Kubewarden and its mission controller. So I already pre-installed Kubewarden in my cluster here. And let's now create an admission policy from the Kubewarden marketplace that forbids to run pods inside of the default namespace as root. So no root user. And in the settings, I want to say pods must not run as root, and I may allow any group though for the sake of the demo. Now, this admission policy will be deployed, and while this is being deployed, let's actually look at the create screen here again, because there's tons of other policies that are directly available here from the marketplace. So we can, for example, limit host pass volumes, we can limit pods to not be privileged, we can limit capabilities, we can enforce AppArmor profiles, we can limit the allowed registries, tons of different things where there are policies already. And if that is not enough, you can also always create your own policies and also deploy them through NeuVector. Policies are distributed as OCI artifacts and written and compiled in WebAssembly. And you can write them in the programming language of your choice. So now I have my policy active. And if I go back here to my sample application, and if I just delete this pod so that Kubernetes triggers that it will be recreated, you can see now that Kubewarden will say, no, running things as root is not allowed, you should fix it. And with that, we can even enforce on deployment level to not have insecure configurations running. So let's go back to the slides and recap. What did we do? We completely hacked into a live application with multiple security vulnerabilities, and without patching anything, we protected ourselves against this with NeuVector and Kubewarden. If you want to know more about Kubewarden and NeuVector, here are a couple of resources, and there's also here a link to the GitHub repository that details how to set everything up for this attack. It has the vulnerable application inside, and it has all the details how to execute the attack as well. And with that, thank you very much and enjoy the rest of SUSECon.